Hey guys, welcome to Structural Madness. It's been a long time since I uploaded a video or actually penned down a blog post. So I decided why not make a short video on something that I feel will be very useful to a lot of people out there and may help answer some questions, very fundamental questions in seismic analysis and design. So here we are going to talk about um, the generation of response spectrum. Um, the figure is mostly familiar to everyone, where we have a response spectrum that's specified by building codes, which varies on the basis of site conditions as well as the distance from the nearest fault. Um, Usually, if you have a fault right there and a site here versus here, what happens is, as soon as this fault erupts and seismic waves propagate in this direction, it actually goes in both directions, but as they propagate, the site that is closer to the fault will experience a very large shaking versus the site that's farther away from the fault. The intensity of shaking reduces, and that's because of energy dissipation of the earthquake in general. Um, That's true in most of the scenarios, unless you have something called a basin, where you have a site or a large area or an entire metro area like Seattle, where it is lying on a relatively soft uh, base compared to its surroundings. So, for example, what happens in Seattle is the Seattle has glacial soil, but it's sitting it's kind of a bowl that is filled with jello in a way. So you have relatively softer soil underneath the entire greater Seattle area versus rocks and mountains that are present in the vicinity of it. So if you look at some sites that are right outside this basin, their intensity, the shaking intensity, because of this particular primary source will be fairly low. But as soon as you look at a site inside the basin itself, the shaking suddenly gets amplified by a factor of like 4 or 5. In case of Seattle, for an M9 earthquake, if you look at a site outside of Seattle, the shaking intensity is extremely low and it kind of possesses no threat in a way. But as soon as that shaking gets filtered into this basin, it kind of amplifies so significantly that now all of a sudden it's posing a big concern. Anyways, we are not going to talk about that, but just wanted to throw out there how earthquakes can kind of change their magnitude in a way, or their impact based on what are the surrounding conditions. But let's go back to response spectrum right now and how do we generate it, because that's what we are going to talk about. So usually what happens is we see a lot of these accelerographs that are these kind of in shaking in intensity. Now, these graphs have certain values called PGA, also called peak ground acceleration. And these big peak ground accelerations are based on again what are the site conditions and distance of fault. So again, farther away you are, your PGAs will start dropping down. So now, every earthquake has certain characteristics. Some earthquakes are very high intensity, high frequency earthquakes, versus some are relatively low intensity, low frequency earthquakes, and it can be a mixture of anything in between. And that creates different kinds of response into different sorts of buildings, like earthquake that's farther away from the fault and um, a building that's located in a relatively softer soil. So a taller building is going to be impacted more compared to a shorter building. Versus if it's a very hard soil, again, the same source distance, then a relatively shorter building is going to impact more because that soft softer soil kind of reduces um, your intensity, not intensity of shaking, but kind of the frequency of shaking. So the soil itself filters the shaking that's coming in, and now the building that's sitting on top of that soil is is kind of exposed to that modified intensity, right? So that's how natural characteristics play. So using this particular accelerograph, how can you go from here to generating something like this for different sites, right? How does this happen? So this happens using some numerical methods that kind of helps us translate this natural excitation into these sort of pseudo accelerogram, which are commonly known as response spectrum. And I have created a spreadsheet that kind of does the exact same thing, and I'm using a particular method called Numark method. And within the spreadsheet, I've kind of laid down overall approach on how the equations are put together and how Numark method comes into play um, to kind of give us the peak response for a particular building. So this is a very general method. You can find it in any structural dynamics book, and it's pretty much explained in the exact same way. I'm not going to go into details because I think the books will do the justice compared to me, as it is mostly mathematical understanding that you need to develop over here and nothing more. But just to go over it briefly, it's like we have our simple dynamic equation that's mass into acceleration plus velocity times its damping matrix plus stiffness times uh, its displacement, right, is equal to what's the load that's applied. And in case of earthquake excitation, the load that's applied is just inertial load. So it's the self mass of the system times what's the acceleration at the ground. And I'm just writing this down in the form of differential equations, and from there on, I just uh, can carry on some certain sets of mathematical operations to simplify the equation such that I can eliminate the mass term as well as stiffness term from the matrix or the equation itself, which is pretty crazy to think about. Like, how do you not have to take into account the mass of the building or the stiffness of the matrix of the building? But the thing is, we are accounting one important characteristic, and that's the frequency, natural frequency of the building. And that natural frequency of the building is accounted for in this particular term, 4 pi square over t over here. So 4 pi square over t, you can kind of replace it with omega square, um, which is the frequency, and t is the time period over here. So that's how it kind of works together. So you are kind of incorporating a natural characteristic of the building, and the time period of the building, natural time period of the building itself is dependent on two terms. One is the mass, the other is the stiffness. That's K over M right there. So inherently, you're capturing the two things together into the natural period of the system itself. And C over M, we are going to convert it into a critical damping coefficient, which is represented as 2 zeta times into omega. Um, anyway, so from there on, all I'm doing is kind of breaking down this equation into I would say small pieces or small formations. So if I take this curve over here and break it into small chunks, you can kind of assume that it's linear in between these segments. It's a crude approximation, but remember that these time step intervals are extremely small. So in the examples that I'm going to show you, I'm actually utilizing a time step of like 0.02 seconds. So that's a very small time step. Anyways, So without going further into the details on how this has been evaluated, this is very easy to follow through and understand. And again, as I mentioned, books do the justice over here, so I'm not going to go in depth over there. But as soon as you have that information on your ground motion time history, what you can do is, based on this particular time history, you can go through this Numark method, and at every natural period, so let's say you have 5 different buildings at 5 different natural periods, uh, you can calculate the peak acceleration or peak displacement value for each of these buildings using Newmark's method. And then from there on, it's fairly straightforward. You can calculate the pseudo velocity, which is nothing but omega times the calculated displacement, or the pseudo acceleration, which is again omega times the calculated pseudo velocity. And if you do that for, let's say, 5 different buildings over here, you kind of develop a curve for your displacement as well as acceleration, because each building again has a distinct time period, and at different natural time periods or frequencies, you'll get a different response. And all you are plotting over here is the peak response of that particular building at that particular frequency when it is exposed to that the excitation that you are taking into account. It is as simple as that. So once you plot those peak responses at each individual natural frequencies, that's kind of presented here in this curve. So once you do that, you get a graph, and this is nothing but showing you the spectra of responses called response spectrum, right? So if it's a displacement spectra, then we call it displacement response spectrum. If it's a velocity, then it's a pseudo velocity spectrum. If it's acceleration, then pseudo acceleration spectrum. And that's pretty much it that we are going to look at today, right? So let's go further up over here. So what I'm doing is, this is the input ground motion, and again the time step is just 0.02 seconds. This is just a random motion. That's the image of the motion is right here. All you do is kind of, once you press this generate here the response spectrum, then what the spreadsheet is gonna do is, using a few macros, it's just going to calculate the peak displacement spectra for you. And based on that peak displacement spectra, it can calculate the pseudo velocity, which is again just the natural frequency um, at, of that particular element or building at that instant that you are taking into account, multiplied by its peak displacement. And same thing with the acceleration. It's the natural frequency of the building times its calculated pseudo velocity at that period. And you can do that for over the entire band over here and calculate your entire spectrum. Um, what's interesting over here is, as we expect, the lowest damping value is gonna generate the highest or maximum possible response. So at 1% damping, it's generating the most amount of displacement, because the system cannot dissipate as much energy that it is kind of absorbing in from the earthquake. But as the damping is increased, your response kind of goes down. So that's why when the building is old, and if you have to retrofit, and there is no way you can increase the strength of the system or displacement capacity of the system, then you kind of install some viscous dampers. And what those viscous dampers do is they increase the damping of the building or the system and reduce the peak excitation of the system itself. So that's how it generally works. And I've covered it in one of my blog on resonance and damping, and I'll share the link in the description, video description below. Um, Similarly, if you're interested in actually plotting the curves or the graphs for a particular system with a particular natural frequency at a certain damping, you can do that too. So for example, you want to plot a building response at 2.5% of critical damping, and the natural period of the system is, let's say, 3 seconds, then you can generate that entire uh, displacement history, velocity time history, and acceleration time history for that particular system with a natural period of 3 seconds and a damping of 2.5%. And remember, the velocity and acceleration over here are not pseudo velocity and pseudo acceleration. These are the actual calculated velocities and accelerations. And these two will be definitely different because pseudo velocity and pseudo acceleration are kind of an approximation of expected or um, uh, you know the damping that we have, it's kind of just an approximation of what the expected velocity could be. But the time history curves that you are looking at here, these are giving you the exact values of velocities and accelerations. And I'm just gonna share this file with everyone. So if you are just curious on understanding how different kind of motions affect different buildings, then you can just run this spreadsheet through multiple times and see different kinds of responses. Let me just give you an example. So for example, let's look at this displacement versus acceleration spectrum. You see something very interesting is at shorter periods, it's acceleration that's very high in the buildings, and with longer periods, it's your displacement that stays fairly high compared to acceleration. And this is quite important to understand fundamentally if you are designing buildings for any earthquake. So what happens is the shorter the building, the more violently it kind of accelerates because again its natural period is so low and it's closer towards what could potentially be the natural period of the earthquake that's coming in. And and it's just the natural tendency of the system. Like if you take a shorter inverse pendulum, then you have to shake it kind of very violently back and forth, and the response that it generates is also very violent because its time period is so short. Versus when you look at a longer time period buildings, they go very slow back and forth, but they displace so much that they demand a lot of ductility from the system. So you must have heard a lot of people, amazing structural engineers, always talking about like tall buildings, how they are important to design for ductility and kind of peak displacements, and they are generally displacement and drift governed rather than the force governed. And this chart exactly shows that they may not experience significant accelerations, but they do experience a lot of displacements in general. So you have to focus on ductility and how much can your building drift. So a lot of tall buildings are designed to drift for like 2.5%, while a shorter two-story building, it's not even gonna see like a 0.5, 0.6% drift if it's kind of designed and detailed properly. So that kind of gives you a very good insight on the different sorts of responses the building may possess at different periods. Um, anyway, so here's an interesting earthquake. What this earthquake is an M9 earthquake that's going through the Seattle Basin. So as soon as I finish plotting this, it's a very large earthquake. It's lasting up to like 5 or 6 minutes. So that's why it takes a little bit longer to process. But since this particular record is within the basin of the Seattle metropolitan region, the frequency is filtered by the Seattle Basin, as we were talking about right here. And the natural frequency of the Seattle Basin is about 3 seconds or so, if I'm remembering it correctly. So what you'll see now is towards the longer period as well, there is significant, like relatively significant acceleration compared to the peaks over here. But what's even more interesting is look at the displacement demands on the system. Because this is in Seattle Basin, and since the earthquakes frequencies are filtered in such a way that it's now closer towards the natural frequency of the basin, which is like slow 3-second back and forth sloshing, it kind of impacts significantly the taller buildings or the long period buildings compared to the short period buildings. So this is how a different kind of excitation bring a very different perspective into your structural designs and detailing. So yeah, this I feel like this tool will be very helpful for everyone, and I just decided that maybe I should share it with you guys if you want to use it. But yeah, that's pretty much it for now. Feel free to comment below and let me know what next would you like to see. I'm trying to get back again in creating more videos, and I may share more tools and spreadsheets like this moving forward, which I feel is very insightful and helpful for everyone to understand rather than just conceptually talking about a topic. So if you like this approach, just let me know and we can move forward with this, or else maybe I'll be fine-tuning my approach based on your recommendations. But no, thank you for tuning in, and I'll talk to you guys soon.